Imagine opening a project file you need to update by Friday, only to find this, a dense block of code that doesn't read smoothly from top to bottom, but instead marches relentlessly to the right side of your screen through layer after layer of indentation. Developers refer to this specific architectural anomaly as Callback Hell. Others simply call it the Pyramid of Doom. Encountering a block like this means you are looking at a fragile, tightly wound system. Reading the logic gives you a headache, making a single update feels like defusing a bomb, and tracking down a bug is difficult because every line strictly depends on the block wrapped around it. This shape is rarely the result of poor effort. It is a structural scar left behind by the way early web development attempted to manage the concept of time. To understand how code gets this messy, we have to look at what happens when a web browser needs to wait for a server to send a piece of data, like an image or a weather update. This diagram shows synchronous programming. The browser executes instructions sequentially on a single track. If a command takes 2 seconds to fetch data, everything stops. The interface freezes until that task finishes. Asynchronous programming provides the alternative. The slow task moves to a parallel background track, keeping the page interactive while data arrives. The original tool built to handle this delayed response was the callback. You write a function, hand it to the background task, and tell the computer to run those instructions only after the data arrives. While callbacks handle one isolated task well, they create a problem the moment a program requires a sequence of tasks that depend on each other. Consider a routine login sequence. First, the server searches for the username. Then it checks the password. Finally, it loads the user profile. 3 dependent steps. We map out that first step by asking for the username and attaching callback1 to handle the data whenever the server finds it. We cannot check the password until the username confirms. To enforce that timing, the second task and its callback must be placed inside the boundaries of callback1. Loading the profile relies on the password check, so task 3 and callback 3 are written inside callback 2. Enforcing this sequence of time using basic callbacks forces the architecture of the program to grow horizontally. Every dependent step pushes the text further toward the right margin. In practice, developers need to track what is happening at each of these steps, so they add diagnostic print statements to log the data as it arrives. When you inject those basic tools into the nested functions, the code expands. The actual instructions are buried under a thicket of brackets, parentheses, and deep indentations. We naturally read text from top to bottom. But this nested structure forces the human brain to read the logic from the outside in, holding multiple levels of context in mind just to understand a simple sequence of events. This nesting creates a severe cognitive barrier. It hides logic errors behind a wall of brackets and makes the system nearly impossible to debug effectively. To fix this structural nightmare, the JavaScript community introduced a new architectural tool, the promise object. Instead of deep nesting, a promise returns a placeholder, a contract that data will arrive. Developers use .then syntax to chain these contracts. Task 1 triggers Task 2, flattening the sideways pyramid into a readable vertical list. Promises realigned the code from horizontal back to vertical. However, programmers still had to manage their logic inside specific .then blocks to handle these delays. The final architectural refinement arrived with 2 specific keywords, async and await. Placing the word await in front of a network request tells the computer to pause the local function on that line. It waits for the data to arrive automatically, without requiring extra callback functions. This side-by-side comparison shows the result. On the left is the dense, sideways pyramid of Callback Hell. On the right, the exact same logic written with async and await. The code is sleek, flat, and reads clearly from top to bottom. The machine still performs the same background waiting, but the developer can now write and read these instructions as a simple top-to-bottom sequence. The shift from the sideways pyramid to a vertical list acknowledges that while machines easily process deep nesting, humans need a linear path to follow. Writing great software is as much about human navigation as it is about machine execution.